Yes, and I've also read reviews, and it turns out people are paid to make reviews, and they will lie. Yeah, I know. I was shocked myself. People lie on the internet. That clearly can't be true. Which is clearly irritating.
It's a nice job, though. You get paid for, like, say, this is good, this is not good.
Yeah. I mean, everything is ruined as soon as other companies get involved. I used to be able to go on Reddit and I would just say, this device, Reddit, and then you would get people like, I just bought this the other day, this thing is crap, and here's why. Or I just bought this, I've been using it for 2 years, awesome, you get good reviews. You know what companies now do? And this is like, you can get this as a job. You become a user on Reddit, you're part of their social media team, and you'll just come up, hey, I've had these shoes for 3 years, they're fantastic for hiking, and show pictures, and their sales will noticeably go up because that people think it's an authentic review. It's just a paid for advertising.
I mean, it's easy money if you get
It's easy money. Yeah.
I would do that.
Yeah. And then for a while, TikTok was the same way. And now it's not. So I would like you to go out there and invent a new social media. We probably have a year or two before the companies jump on board because it will confuse them. So go out there, invent something wild. Wild.
Which had two.
Shut up, it's worse.
Which had two, I mean,
What?
no.
There's business here about
There was a time that Facebook was actually cool. And now it's just old people screaming about politics. Most of those are my relatives. Timmy, Ben, Jonathan,
Facebook
Ariel,
Get a little golden
Zoe, Lisa, Felix. Hold it. Did I actually see Jonathan? There you are. Zane, Matthew, William K. There you are in the corner. Alejandra, Birdie. Birdie. There you are. Zachary's not here. Kieran, you're leaving 10 minutes early? We have a quiz.
Yeah, I'll stay for the quiz, though.
William R. is there, and Naomi is not and should not be, and Hugo is here because he talked to him, and Sahir is here. Excellent. Now, I'm done all the things. You have your notes out? Do I have an extra? I probably do. But where it is another trouble. Please get out your periodic tables. You should have out your notebook. Last day, I think we were coloring, were we not? Really good day. Simple Alex Jamie, who needed another packet? Who needed another packet? Put away your computers, please. Computers away. Okay. We were here last day. And did we finish coloring that in? Did I label all the things? I don't think I did.
You have these 7 metals.
Metal separated.
I think you showed us the more.
I think I had it up and then the bell went.
Sorry, can I get a pen, please?
Yeah, they're over there on the back. So these, what are those called?
Metalloids.
Metalloids.
Okay.
You can also call them the semi-metals. I am going to have to get used to writing with this because I think it's even worse than before. Then everything over here is what?
Non-metals.
Non-metals. So this, scroll it down.
What are those?
Those are the non-metals. Yeah, my writing has gotten. There we go. And then everything else in the universe on this table is metals. And a metalloid just means it has properties of both metals and nonmetals. You can sometimes get them to switch. Silicon is one. That's why it makes such a good, it's a great metal to use in computers, because it conducts electricity, but actually not super well, which means they can do things with it in terms of its resistance to make computer circuits that you wouldn't otherwise be able to do. And it has properties that makes it useful to be able to just print out circuits. Whereas copper, you know, straight metal. So, and being able to know the difference is going to be important for our naming. So in terms of practical experience, where are all the positive ions?
Yeah. Yeah. Metals
Metals.
are likely more
Yeah,
likely to be plus.
these are positive. These are negative, usually. And then these could be either, depending on what they're doing. Yes?
Hydrogen is not metal.
Ah, hydrogen's not a metal. Excellent.
But it's
So what is hydrogen?
It's gas. Yeah,
It's a gas. Interestingly, if you put hydrogen under enormous pressure, it will behave like a metal. You can actually get metallic hydrogen. However, you need the pressure available to you at the core of Jupiter, which, you know, we don't have.
Maybe they do.
But, yeah, why do we put hydrogen there then? Yeah?
Just easy. Atomic number is just one.
Yeah?
Just one.
But you can find lots of periodic tables that will actually put it here where it belongs.
Wait, I got a question though. 'Cause
Yes?
you're saying-
Is it because it's positive and the positives are on this side?
Yes, it's because if it is to get a charge, it can go positive or negative, but like 95% of the time it's +1 like everything else. This is all +2. It can be -1. It's just most often isn't. Matthew?
You're saying that it's not a metal because usually you find it in the gas form,
Yeah.
but all the rest of the metals can also be gas form. It's just depending on what state it is.
No, in the gas form, there's still metals. In fact, if you get an atomized, a gaseous metal, can you make those conduct electricity? If they're moving fast enough, you might be able to, because they'd like to form a charge. But no, there's still metals. Because you mentioned state.
Yeah.
So, iodine. I don't want to ruin this. So maybe I'll do it with another color. I am going to, all the things that are, do I use blue? So this is solid, that's solid, and everything on here is solid, except for, what's the liquid metal?
Oh, mercury.
Mercury. So this is a liquid,
Sometimes.
and gallium is sort of, you'd probably call it a liquid, because if you get, I've had pure gallium on my hand, heavy metal poisoning, but I had it on a glove. It will melt in your hand. Its melting point is just slightly higher than room temperature. So it's, most of the metals are solids. It has to do with how they undergo their metal-metal bonding, but they don't have to be. If you heat them enough, they become a gas. They don't become a non-metal. If you cool fluorine enough, it will become a solid. It's still a non-metal. It's still, if you make chlorine solid, it will not conduct electricity. It will not conduct heat. If you take a metal pan out of the oven and you touch it, you're going to get burned, which is why you have gloves made out of carbon, often. They're cloth, so there's lots of carbon, and it's an insulator. So these tend to be insulators. So all the metals tend to be conductors. All the non-metals tend to be insulators. And imagine if you had metal gloves. Would that be a very good idea? Other than the lack of flexibility?
Well, depending on the sport.
Yeah. What does positive? That's a plus sign. And that's a negative sign. I tend to use plus and minus than VE between positive and negative because it's faster. So that is just a little thing that's my fault. Where are the positive ions, where are the negative ions? I think that's all from there. We've got metals, metalloids, non-metals. We've got this side as conductors of electricity and heat. These tend to be insulators. If you have a pot and it has a wooden handle, often safe to grab. But if you're heating up a cast iron pot on the stovetop, and then you go to grab the handle, it's going to burn you because that's a property of metals. It conducts heat really well throughout it, as well as electricity. And these, you can play around with properties of both depending on what they're doing. So we're going to start off with bonds, ionic bonds. What I would like you to do is down here, something we've already done and we know how to do. I want you to give me some Bohr models of the atoms of sodium and chlorine. Leave yourself a bit of space so that you can draw them twice underneath each other. So we want plain O and A and plain old Cl. If you're like, I don't like Bohr models, I mean, a Lewis dot diagram would be fun. Oh, we got that. What do you need? What's something right now? Okay, you have a periodic table, right? How many protons does sodium have?
Sodium?
Na.
23.
23. So you can start off with that. Hold it. It doesn't have 23 protons though. How many protons does it have?
12.
12. 12? 11. That's okay. It's a bit stressful when the person's standing right there. Well, you said it was 23, so how many neutrons would it have?
12.
12. Excellent. So we got that. How many electrons in the first shell?
2.
2. And how many in the second shell?
8.
8. And now I'm going to totally switch up colors. No, I'm not. I'm just going to change my placement. How many in the last shell?
2.
1.
Why'd you say 2?
This is 2. Should be 1 because I used 12 to minus.
But it's based on the number of protons. So if you use 12, that makes sense. So only 1 electron. Right? And then we'll just wrap that all the way around. And visually, I'm finding this kind of annoying because I can't tell where the nucleus is because that's a lot of circles, so I'm just going to do that. Oh, weird. You put yellow on pink and it makes red. Okay. Now, who else? Good. I'm just seeing out. Does anybody else need a guided tour? Laptop closed. No, it's good. Okay. So you're drawing Lewis diagrams. Play along. You'll be. It's exactly the same. So chlorine. Since now everybody's got that far. How many protons? This class. How many protons? 17 protons. How many neutrons?
18.
18.
But isn't chlorine, isn't it weird that way?
Chlorine is 35.5, so you'd estimate it to be 36. 36 minus 17 is 19, I think. Well, I'm saying that because you said that. 36, yeah, it would be 19. And if anybody has done it in their calculator and they know that 17 plus 19 doesn't equal 36, let me know, because sometimes when I'm over the board, my math goes strange. How many in the first shell? 2. Second shell? 8. And now it's the part where you're probably going to get annoyed at me. 7, but I want you to draw it like this. I want you to draw it like a Lewis dot diagram. So I want you to draw it as electron, 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 electron. In their pairs, they would normally be with only a single electron. Then we can connect. Now this, what I'm about to show you, is often said, this is ionic bonding. This is not ionic bonding. This is what happens just before ionic bonding. Chlorine looks lovingly across the room. Sodium looks lovingly back. And sodium says, those are nice electrons you have. Would you like another one to complete the set? And this little Joey electron walks on over to chlorine. It's so romantic. Now, if you do a Lewis dot diagram, your new Lewis dot diagram for sodium, once you do that, like on your page, can you grab it and then move it over? No, you can't. So you have to do it again below it. So you have to draw 2. Now, for the second one, I am going to do the Lewis dot diagram, which is just going to be, what did I do? Pink? It's just going to be Na, NCl, 1, 2, 3, 4, 5, 6, 7, 8. But what happened here in terms of their attractiveness? Yep.
The reason why they share electron, the reason why electron was given is because they're attractive.
No, they weren't attracted before. Now, before they were unstable, they were high energy, and now they are low energy. And I know oftentimes high energy and low energy is used to indicate that things are, high energy is good, but low energy is just really stable. So before they were high energy, it gave it away. That wasn't a bond. They weren't attracted to each other, but now they are attracted to each other. What has changed? Why are they attracted to each other? Pardon? They're both now stable. They're both now low energy. But what does sodium now have that it didn't have before?
A charge.
A charge. What's the charge in sodium?
Plus 1.
+1. So now this whole thing is +1. It wasn't before, but it now is. What's the charge in chlorine? -1. And that +1 to -1 is the attraction. You've heard the phrase opposite attracts? This is where it applies. It applies to this and magnets. Just so you're aware, it does not apply to people. Every romantic comedy you've ever seen where they're totally different people and then they fall in love, they're divorced in 2 years, guarantee it. They have no common interests, they don't like each other. You know, every relationship has two people. One person is calm, sane, understanding. The other person likes to camp. They shouldn't get married. Yes?
Would it be more attractive to say a -2 than a
Yes.
-1?
Yes. In fact, but it works like you would expect. The -2, so attractive. It wouldn't just attract one of them. It would attract two of them. It now has a posse. So, draw your first one, and then for your second one, you can redraw it with the electrons in the right spot, or you can redraw it, whoa, it's touch. Oh my God, I saw this the other day. I keep forgetting. That is all 5 fingers.
Oh my god.
Every time that happens. Do you know that this has magic pens? Literally has a magic pen. I can just write hello in a magic pen.
What is it now?
And it's magic.
What's magical about it?
It disappeared.
Wow.
So
Oh, that's actually really
you'd have to keep up, and my writing would just disappear after a few seconds. That's why I don't use it. You can also do things like, I can say like, look at this diagram really closely. Or look at only this.
What? Can you draw just around a little along the dots?
What?
How small can it zoom in?
Good point. Oh, that's not zooming in. You want square zoom. Oh, yeah, that's kind of silly. Yeah. I also have, although I don't use it, I have a text pen where I can do that, and it should go.
We can read the writing.
Magic.
We'll see. Anyway, that's not the point. I'm getting distracted because I have a new projecting thing, and that's fun. So you can redraw them as either Bohr, or you can redraw them as Lewis. Lewis is probably a little easier, and this probably illustrates why we use Lewis, is because we can show that. But you do have to put the brackets around them to show that this whole thing now has a charge, and this is the ionic bond. So this is a special type of attraction, and this is known as an electrostatic attraction. Electrostatic is just a charge to a positive and negative. It's how you'd have static electricity, is where that gets its name. When you take a balloon, you rub it on your head, you're actually transferring electrons from your head to the balloon or vice versa. Now the balloon has a charge, and when you put it against the wall, it will stick because the wall has a bunch of electrons. And if it's positive, all the electrons in the wall will rush towards it, and now the wall's negative, and that's why it sticks. And the vice versa. If it's really negative, the balloon, and you push it at the wall, then the wall's electrons will run away, and now that area of the wall's positive. That's how static electricity works.
How do you make a balloon negative or positive?
It depends what you're rubbing it with, and it also depends on the material. So certain types of plastics will just collect electrons when you rub them. So that's why when you have plastic shoes, some of them, if you go like this on the floor, and then you build up a charge, you touch someone, you go, zap!
Really?
Yeah. Hasn't that ever happened to you?
No, yeah, but I didn't know you can like charge
That happens to
yourself.
my hair.
Yeah. Yeah, and that's all the electrons coming in your hair. They're all getting the same charge, and they're lifting because they're now repelling each other. Yeah. Okay. So electrostatic attraction is the attraction of a positive and a negative. That's what that is. attraction of positive, negative. Okay, good. Everybody good? Go. Don't throw a essentially small spear up into the air while also looking up. Yeah. I mean, you have glasses, but Hugo, later on the day, like, ah! No, Hugo's blind in one eye. Bertie, what do you, okay, what is next block that you're studying so hard?
Lunch.
What is on that? Are you playing games?
No, I was using this on. I could do Google Docs.
Okay, but if you don't focus in this class, then you won't be done this homework. I am sympathetic, but not that sympathetic. Okay, so Lewis diagrams. We did this. This is stupid.
I almost got it.
We did this. What I would like you to do is of
Almost got it there.
Lewis
Goodness.
of K and CL.
Damn.
And I want you to label, we'll define in a moment, label the cation, the anion, where the electrostatic attraction is. We are going to define an ionic compound, show the ionic bonds. We're going to discuss what kind of things make ionic bonds and which ones they are, so you can tell them apart. So, do the Lewis and KL. Oh, darn. I keep touching the board. Paw prints! Paw prints. That's pretty awesome. I probably shouldn't be touching the TV. IT's already mad at me. Like, I open up my Google Drive and it just has a big red mark. I'm allowed 50 gigabytes on the school Google account for as a teacher. I have 2.97 terabytes. In my defense, I used to have 15 terabytes and I got it down to that.
Can't you just,
You have to be.
couldn't you just put it onto a separate, like you could just then like,
Let's just say I back up anything I've ever seen. Or heard.
I mean like, it's fairly cheap to get.
Okay, doing this.
Get
And include as many, include as many of each as you need. So you may not need just one. Hold it. That's stupid. I've changed it to N. That way that makes sense. Yeah.
So I didn't know we had it before, but how would we and also this
I'm going to flip back for a second. So that's on the previous page?
yeah.
So the brackets go around each one individually. So for Lewis, they go like that. So you wouldn't bracket them together. And this area, that's where the electrostatic attraction is. It's now N.
Where's the ion?
Oh, you can't.
Do you remember from last year? Then just draw it and see how far you get. This is also where when everybody gets as far as they can. I'll take this. Run the next page. Drawing K and N.
What's that?
K and N.
Oh,
On there. Use a pencil so you can erase things.
my pencil was really.
Your pencil was what?
You want us to show the ions?
I want, yeah, the ions. Well, it says atoms and then ions. So draw the atoms first, then the ions, and then as many ions as you need. I have two?
Mr. Newton, we need like 3 keys for one county.
I don't know why I have two.
Wait. Yes, I know it's
So like. we
What?
Is it?
Is it?
need keys for one county.
Okay, here's our first definition. Then. What are charge or cations?
Positive.
Positive. And we know that because cations are cats. And they're positive. Huh? And this is the best I could come up for anions. Anions are like onions. And onions make you cry. So they're negative. I don't know if that's the best analogy in the world. So cations,
I'm sorry, I can eat a cat
an ion with a positive charge. Anions make you cry. They're so negative. Yes.
The thing we just did. These are perfect because they have. This has a minus these.
No, that's minus 3.
Yeah.
And that's plus 1. What do you do? You get 3 electrons. Because you've got 1, 2, 3. You can only take one from there and there.
There's more.
There you go. Yeah. Oh, both. So you'll need 3. You don't have to know those.
Whatever. Then.
You have. Excellent. Lewis diagram. K&N.
This is the same. Like, we can add
And I think it's negative.
Anion is negative. Cation is positive. Pause.
Wait, what did you say?
So now that you have that, do it again, but make the ion.
This show, this
Using as many of either K or N as you want.
3 Ks.
periodic composition.
No, you have to look at it. So what we did before. What we did before, right? You would have had something like, wow.
There's the unequal button right there. Just need a bottom left.
Oh yeah, it is. I should press that. Before, you had a probably something like that. No, you had something like that and like that, right? What? You were asking me how to do the next one. You had this one and then that, right? And then you moved that to there.
To balance it?
Right. How many of you need to do that again? Using as many of each as you need.
So I can just give an extra
3 Ks.
You can, but if you need extra electrons, you have to add more sodium. If you need more receptors, you have to add more chlorine.
So I just want to add more Ks.
Add more Ks. There you go.
Okay, like maybe we can do like
Yeah.
3 K. And this then is also
Wait,
this
so
Yep.
let's say I took and I had like 8 Ks.
Yeah.
Then I have 1 K, like I'd have 7 Ks that go plus 1. Then I'd have 1 K that's minus 7.
But they wouldn't all be, K wouldn't be minus 7.
Wait,
And it's so because
if I had like 8 Ks.
Yeah.
Right?
But
And 7
when K gives up an electron, it becomes positive.
Oh, sorry. I have 7 positives
Right.
and 1 negative.
Negative.
That's
That negative can only, if that negative can only take 1, then it's only going to take 1.
we can
You will have to add more chlorine.
Yeah, let's say I had
We can do both.
no, I just had like a bunch of Ks.
Yeah.
Right? Could they all just give their electrons to 1 so a bunch of them are stable?
Well, it will only accept as many as it can hold. Yeah.
so can we use like this?
Yeah, except, what's in the, oh, you put 3 there. Yeah, that works, but I wanted you to show the Lewis dot diagram. So you wouldn't put the 3 in there, you put the 3 on the outside.
Oh,
And I'm going to show all 3 of them. Okay,
I got a question.
yes.
I guess.
So because I added 3 Ks with that 3 plus 3, I mean minus 3.
So overall, it's going to, well, you had nitrogen. What was the Lewis dot diagram for nitrogen?
Like there's 2 dots on top. One to the right,
That's good.
one to the bottom, and one to the left.
Yeah, so you add something like that, and then you add K, and I'll just get everybody else, because now we're doing it on the board. How many dots do you have in K?
One.
One. So you can only transfer that one over here to make a pair. So how many more of those do you need?
Three.
Three.
I mean, like
See,
two more.
two more, three in total. So you're going to go like that. And then they're all going to each give one up.
Yeah.
So then you end up with N. So it's happy, but what's N's charge? If it's accepted 3 electrons? Negative
Three.
3. And each one of these is just K plus 1. And you could write that as 3K plus 1 and minus 3. Right? Now, if we were to write this as a formula, how would we write that? Where would we put the 3?
Before the K.
We would not put it before. We use that for balancing.
No, K.
Oh, K,
After.
3,
Yeah.
and
How many N's are there? There's just one N. So we wouldn't write the 1 because we don't write ones. It is minus 3, but we only have one of them. So that's why we write the formulas. This number always refers to the number it's, and that's why we can't change that, because their charges are fixed. So we can't change that word while balancing, because that is what the compound in is based on its charge. We can only do this in front when we're balancing. So that refers to 3 potassium.
Could you just have?
Yes?
Can we label that ionic bond?
So this positive to negative, so let's go through this positive to negative, plus 1, 2, plus 3, that is the plus 1. That is the ionic bond. That is the electrostatic attraction, the positive to the negative. So you could point right in the middle there and just say that's the ionic bond. But the key part is knowing that's the positive and the negative.
But it's the same as an electrostatic.
It is, that is, an ionic bond is an electrostatic attraction.
Can you just have 2 ends that are connected, but they just share 3 electrons?
Yes, but that's a covalent bond.
Oh, okay.
That's not an ionic bond. We'll do those next, or soon, not next. What did I want you to label? So we've done it. Which one's the cation?
Okay.
See here, which one's the cation?
The cation, the positive one.
Excellent. So we've got our cation. What's our anion?
The negative one.
Negative one. So there's our anion. What else do we need to label? We've got cation, we've got anion. The electrostatic attraction is the bond. So that's the ionic bond. That's the electrostatic attraction. Good. Sorry, my writing seemed to get away from me at that moment. Electrostatic. Let's see what it says. Oh my God. It recognized my writing.
Or take a listen to it and
Yeah.
just write what you said.
Ooh, I did ionic bond. I didn't do ionic compound. What kinds of elements make ionic bonds?
metals and non-metals.
On average, metals and nonmetals. So, an ionic compound is a metal and a non-metal. And that is about 99%. There are exceptions, because really, does it have to be a metal and a non-metal? What does it have to be an ionic bond?
Metal.
No, it doesn't have to be a metal. You need ions. So an ionic bond needs ions. It needs a positive or a negative. It needs a positive, or to use our new terminology, you need a cation and an anion.
So if it's, so you can have an ionic compound that doesn't have any metal, so you use hydrogen.
I'll give you an example of one. An example of an ionic compound without any metals is NH4Cl. You've probably used this. You will find it in cleaning fluids. It dissolves really well in water. It's ammonium chloride. And the reason why it's an ionic compound is because this is what we're going to introduce later. Did you do polyatomic compounds like that last year?
Yes, I
Yeah. So we have NH4 plus. And we Cl minus. There's nary a metal to be seen, but we have a positive and a negative, so it makes an ionic bond. Now, is NH4 an ionic compound? No, it's a covalent compound. So you have a covalent compound that makes an ion that then becomes a part of ionic bonding. And then next year you learn that the electrostatic attraction between ionic bonds is only one type. And you have covalent compounds that actually have a kind of positive and a kind of negative side, and they undergo what's called hydrogen bonding and dipole-dipole forces. And it's the forces that are keeping your paper together. So there's lots of interactions that go on. But we'll leave that. We'll leave that part to next year. This year, cation and anion, ionic. If I asked you what an ionic compound was and you said it's always a metal and a non-metal, that's fine, especially for grade 10. Fine. I don't know why, but I had the page down twice. So that's just dumb. We did the Lewis ions. We've now done compound. What kind of elements? What is the charge of an ionic compound? What is the charge of K3CN? The whole thing. So what is the charge? What is the charge of this whole thing? It is not 4.
-2.
It's not -2. Hands up for -5, -4, -3, -2, -1, 0. 1, 2, 3, 4, 5. Plus infinity. I am infinitely powerful.
Oh, it's 3.
If I take 1% of my power and put it into a sword, how powerful is that sword? It's infinitely powerful. 1% of infinity is infinity. This is a charge of 0. What is the charge on 3 of the kegs?
+1.
The 3 of them.
+2.
3 of them? By 3, each one individually is +1. By 3 of them, what's the charge? +3. And what is the charge on the nitrogen? Just one of them.
1.
Not 1.
-3.
-3.
Oh.
So together they make big fat 0, and all ionic compounds have 0 charge because they always have to match. Otherwise they keep grabbing partners. Nitrogen isn't going to be happy until it has 3 people living with it. They have a very complicated household. Potassium isn't happy until it has all the negative charge it needs. Now, nitrogen is a little too much for them, so they bring along some partners. But once you put it all together, 0 charge for an ionic compound. The whole thing does. The parts do, but the whole thing never does. So, what is the charge of a compound? 0.
But isn't it still a compound? Let's say you only had 2 Ks in one end. Isn't that still an ionic compound that's just incomplete? It still wants to have a partner, but at that point it's still an ionic compound.
You are thinking too hard. Because when you look at the end of a reaction, it's incomplete, so it will keep going. So you're looking at it in the middle of a reaction. And so, yeah, we would say there's some ionic attraction going on. But the actual stable ionic compound won't happen until it's over.
So you're saying that it'll just keep reacting if there's only 2 Ks in one end?
Yeah.
It'll just infinitely react?
It won't. Eventually it'll stop. If there's more of one than the other, then it will go grab other parts. So we are, you know, in physics when they don't consider things like friction,
Yep.
there's a ton of reactive nitrogen around. If it runs out of K, it'll grab it from whatever nearest partner can do it. And if not, it'll bond with each other to make N2.
Okay.
So it'll do what it needs to do to become stable. And we're not going to look at like all the different things to do. But we will just look at best case scenario. Make sense?
Yeah.
Okay, last one. What holds it together? The electrostatic attraction. Oh! The other part, this last one is what holds it together. If this is Na, what time is it? 12:43. I wanted to get your quiz by 12:45. So we are going to stop there. Quiz, put away everything, get out your pencil. And you can get out your own beer at the table. I was referring you to in case you need to change yours.
Oh my days,
And spread out in the classroom.
I remember.
You're gonna pass. You are gonna pass.
Jimmy,
You're gonna pass. Time to lift your
Sam, and Jonathan.
You're gonna pass.
Jonathan.
Don't think you're not gonna pass.
Zoe.
You're not going to pass. You're not gonna pass. You're gonna pass.
Lisa. Felix. Zane. Matthew. William K. Alejandra. Bertie. Please make sure you're spread out. Gentlemen, you're too close together. We need to spread out or move to another desk or. Pardon? Not here. Kieran. William Run. Naomi. Hugo. Say here. Here. There. We need people to move across more. We still have two people right next to each other. If you could move over one. Why don't you pull your desk out, like about halfway here. And if you can work right here then, and there, and that's fine. Ariel? And Jonathan? Please put your books away, your binders in your, in your bag. On your sheet, there's a spot at the bottom. It says version 1, 2, 3, 4. Put down which version you get. It's right there. Put it on there. And do write your name on this. It's just going to be multiple choice. You can balance it right on it for balancing questions. You can write all over it. You're going to get it back. That way you can have it back to see the questions and you later get the answers for study purposes. can definitely put that.
And I was there like this.
Does anybody else need a periodic table?
Yeah.
Thank you. No, it's mine. As we are just before lunch, once you are done, you can go.